Hello! With this video I would like to present to you a project I've been working on for a couple of years now. The project concerns physics and thermodynamics, which I did not study at the university. So I had to study everything on my own, which costed a lot of energy, but I'm very proud of the result. I hope you like my idea and would like to help me find associates to conduct an experiment.
So the invention I've been working on for a couple of years now is called the climate engine, and it will soon become clear why it's called that way. But first I would like to give special thanks to Professor Michel van Biezen. So as I told you, I had to learn everything myself, so from the mathematics to the thermodynamica, and I did that all thanks to the videos that Professor van Biezen put online. So thank you very much for that. I also needed some values for certain parameters, and I got the values from Engineering Toolbox. But before I explain the installation in detail, I would first like to explain why the installation is useful. So there are two advantages of the installation. The first advantage is that you need 32% less energy to heat buildings in comparison with a normal heating system. And on top of that, there is a little electricity that is produced at 85% efficiency. So very little electricity, but at a high efficiency. So if you take a look at the actual installation, we see that it consists of two vertical tubes. Now, the first tube is filled with water vapor, and the second tube is filled with liquid water. Now, at the bottom of the tube with liquid water, there is a turbine, so it's a classic hydroelectric system. And as the water passes through the turbine, it gets into the vaporizer where it is transformed into water vapor. The water vapor needs to be transported upwards to the top of the tube with water vapor, and then it gets into the condenser. Now, the condenser transforms the water vapor back into liquid water, and during condensation, heat is being released. So during vaporization, you need to add heat in order to vaporize the water. But as water vapor condenses back into water, heat is released. This heat is transferred to the central heating system in our buildings. So as you can see, the water turns into a circle. So the water goes from the condenser back into the tube with liquid water. Downward is transported downwards through the turbine into the vaporizer, and then it is transported up again. So first a quick word about the heat exchanger. So the heat exchanger transports heat from a hot place to a cold place. So in our installation, that means that the heat exchanger provides heating for the central heating system, but it also provides cooling for the condenser. So during condensation, heat is being released, so you have to provide cooling, and the heat exchanger does both things. So as you can see, the installation is an artificial version of the water cycle as it exists on this planet. So every element that exists in the water cycle also exists in the installation. So if we take a closer look at the tube with water vapor, because that is the most crucial part of the installation, we first have to notice that this is a classical vapor pressure setup. Now, what is a vapor pressure setup? In a vapor pressure setup, one starts with a liquid at a specific temperature, so in this case, water at 100 degrees Celsius. And above the water line, there is a vacuum. Now, evaporation starts to take place, and that means that the space above the water line starts to fill with water vapor. This process continues up until a certain pressure is reached, and then the pressure stabilizes. So there's a dynamic equilibrium. And in the case of water at 100 degrees Celsius, this pressure is 101 kilopascal. So 101 kilopascal is the vapor pressure of water at 100 degrees Celsius. Now, vapor pressure is very much influenced by temperature. So, for example, the higher the temperature, the higher the vapor pressure. Vapor pressure for 100 degrees Celsius, as we've seen, is 101 kilopascal. But if we increase the temperature to 200 degrees Celsius, you already get 1553 kilopascal. If we increase the temperature even more to 371 degrees Celsius, that is 645 Kelvin, the pressure increases to 21,505 kilopascal. Now, that is the pressure at the bottom of the tube with water vapor. So that is a choice we make here. So why would we need such a high temperature with an accordingly high pressure? Well, the higher the temperature, the less energy is needed to evaporate 1 kilogram. So as we can see here from a graph from Engineering Toolbox, the energy needed to evaporate 1 kilogram keeps on dropping as the temperature rises and eventually becomes zero. It becomes zero at the critical point of water. So in this installation, at the bottom of the tube with water vapor, we choose a temperature close to the critical point of water. So a third point we need to discuss here is the height of the installation. Now I've chosen the height of the installation at 500 meters. Now this is way too much to be realistic, and I promise you that all at the end of the movie I will show you a way to reduce the height, but it's just easier to prove my point with a certain height. Now the effect of the height is that the pressure on top is lower than the pressure at the bottom. So just like the air pressure in mountains is lower than the air pressure at sea level. So what happens is that the water vapor at the bottom is compressed by the weight of the water vapor on top of it. So the pressure at the bottom, as we've seen, is 21,505 kilopascal. And to calculate the pressure at the top, we use the isothermal formula. So what does that mean? That means that the temperature in the tube with water vapor remains the same. Now the pressure as calculated is 21,198 kilopascal. So as we can see here at the bottom, the temperature in the tube with water vapor is 645 Kelvin, but in the middle it's the same temperature, and all at the top, just below the condenser, it's also 645 Kelvin. Now, the effect of the lower pressure is that you also have a lower boiling and condensation point. So just think of the mountains. So as we all know, at sea level, water starts to boil at 100 degrees Celsius. What is also true is that water vapor starts to condense at 100 degrees Celsius. Now, if you go to the mountains, for example, water starts to boil at 80 degrees Celsius. That also means that water vapor starts to condense at 80 degrees Celsius. So the boiling point and the condensation point is always the same for a specific pressure, but it varies according to the pressure. Now in our installation, that means that as we reach the top, the boiling or condensation point has dropped to 643.7 Kelvin. So that is 1.3 degrees lower than the boiling and condensation point at the bottom. That means that before the water can be condensed, it first has to be cooled 1.3 degrees. So as you can see here, as the water vapor rises through the tube with water vapor, it retains its temperature of 645 Kelvin. And energy needs to be added so as to keep the temperature stable. So as the water vapor of 645 Kelvin reaches the condenser, it first has to be cooled 1.3 Kelvin. Then the water vapor can be condensed to water. As soon as the water vapor is condensed into water, it flows into the tube with water, which is also isothermal, because no heat is added or subtracted. So the water keeps its temperature of 643.7 Kelvin all the way to the bottom. And as it flows through the turbine into the vaporizer, it still is 1.3 degrees below its boiling point. So that means the water first has to be heated 1.3 Kelvin before it can be evaporated. So before evaporation, a thermal correction on the liquid water needs to be done. So now that we've seen all the components of the installation, we can start adding values per components. And all the values are per kilogram. So if we start with the thermal correction on the liquid, because that is your input, that is where we have to add energy. And if we calculate the energy to raise the temperature of water 1.3 degrees using the specific heat of the average temperature, the energy needed for this thermal correction is 32.33 kilojoules. Then evaporation can take place, and evaporating 1 kilogram of water at 645 Kelvin costs 152.7 kilojoules. Now, once the water is evaporated, it needs to be lifted while it retains its temperature. And the energy needed for this lift is equal to mgh. Now, why is the energy needed equal to mgh? I'll put the proof in the description below. Here it suffices to say that the formula for isothermal work is used, but that the fraction of the volumes is replaced with e to the power h divided by k, which you may remember from the way the pressure differences were calculated. And then it goes very quickly. MGH is of course the formula to calculate potential energy and is also the basis for calculating the energy the turbine in the installation will produce. So the turbine produces more or less the same amount of energy as the lift costs. Now there is a small correction that needs to be done, so there is a small inefficiency. So now that the water vapor has risen to the condenser while retaining its temperature, the thermal correction on the water vapor can take place. To cool down 1 kilogram of water vapor, only 2.66 kilojoules has to be taken out and sent to the central heating system through the heat exchanger. This value is a lot lower than the value of the thermal correction of water because the specific heat of water vapor is a lot lower than that of water. So concerning the thermal corrections, we can already compare an input and an output. Now the output, the thermal correction on the water vapor, is a lot lower than the input, so the efficiency is only 8%. So far the installation is not a good idea. So after that the water vapor has been cooled down to its condensation point, the condensation process can begin. And here is where the magic happens, because the energy released during condensation is a lot higher than the energy used during evaporation. So if we look at the efficiency of the phase changes, we see that during evaporation 153 kilojoules is consumed, but during condensation 242 kilojoules is released. So that gives an efficiency of 158%. So we have 58% more energy. Now this might be hard to accept, but as we have seen from this graph, the higher the pressure and temperature, the lower the heat of vaporization and condensation. But in this installation, the pressure and condensation point drops with altitude, meaning that more energy is released during condensation than is used during evaporation. This becomes even more clear if you compare the heat of vaporization and condensation with specific heat. The heat of condensation gets lower with higher pressure, hence higher as the pressure drops. But the specific heat rises as the pressure increases, so drops as the pressure drops, meaning that the thermal corrections have an inefficiency exacerbated by the fact that the heat is added as a liquid and released as a vapor, and the phase changes have an energy gain. Moreover, if we look at the total energy required by the vaporizer, that is thermal correction on the fluid plus the heat of evaporation, we get 185 kilojoules per kilo. If we look at the energy that is released by the condenser, that is the thermal correction on the vapor plus the condensation enthalpy, we get 244 kilojoules that is sent to the central heating system. That means that the condensator sends 32% more energy to the central heating system than that the vaporizer consumes. So if we compare a situation where the heat is sent directly to the central heating system versus when the installation is put in between the heat source and the central heating system, we get the following picture. In a central heating system, water at atmospheric pressure, important, is heated to 70 degrees Celsius. And with the installation, 32% more water can be heated. So if water enters the central heating system at 20 degrees Celsius, the following result is obtained. 1.17 kilograms of water versus 0.89 kilograms of water, or 32% more. So to finish our story, there is still the hydroelectric part. The hydroelectric energy generated by the turbine is very similar to the energy needed to lift the water vapor, but there is an inefficiency. The turbine only provides 4.16 kilojoules. So why do we not get all the potential energy? Well, the reason is that the pressure above the water line after the turbine, so at the bottom of the tube with water vapor, is higher than the pressure above the water line in the tube with water. The pressure on top of the tube with water is exactly the same as the pressure at the top of the tube with water vapor, since a vapor pressure always occurs. So this difference in pressure is where the difference in energy output comes from. So if we compare the input and output, that is the energy needed to lift the water vapor, and the hydroelectric output, we get an efficiency of 85%. An energy gain is of course very hard to accept, so I would like to present an alternative theory. The energy loss in the thermal corrections is equal to the energy gain in the phase changes. Now this is very far away from what the tables indicate and would be a completely new law of physics. Moreover, it provides a way to calculate the condensation enthalpy. So the condensation enthalpy at T2 would be equal to the condensation enthalpy of T1 plus the energy needed to raise the temperature as a liquid minus the energy released as a vapor. Now this is not my possession, but if you believe that this is the way it has to be, at least you will have to agree that an experiment is needed. So this was the explanation of the installation. I would just like to add a couple of improvements that are possible. The first is to have a non-isothermal tube with water vapor, where the water vapor cools down gradually as it rises. This has no effect of efficiency, but may be more practical to build. One can even use condensation enthalpy for lift, since in nature, raindrops also first rise because of the heat released during condensation, meaning no heat has to be added in the tube with water vapor, meaning it's even easier to build, but nothing changes the efficiency. An even more interesting improvement is to put different installations in series, whereby the heat released during condensation of the first installation provides heat for vaporization of the second installation. So the advantage of putting different installations in series is to reduce the height of the installation. Importantly, a different substance is needed for each installation, with each time a lower critical point. So for example, if the first installation has a substance with a critical point of 647 Kelvin, for the second installation a substance can be chosen with a critical point of 620 Kelvin. Important to note there is that the heat source in our installation provides a temperature of 645 Kelvin, but the temperature needed in the central heating system is only 343 Kelvin, so 70 degrees Celsius. So the usable range is 302 Kelvin. In the installation, as discussed, only 1.3 degrees Kelvin is used for the energy gain in phase changes. So we are just getting started here, but I do need help from a specialist in chemistry. And the last improvement is to replace gravity with centrifugal power. So different installations are placed in a circle, and the pressure at the turbine depends on how fast the circle spins.
So this was my presentation. Thanks for your attention. I hope I convinced you that the experiment is worthy to be done. So the more people that watch this video, the better, because I do need some support with the experiment. I've also written a text about it. The text includes a section about entropy, which has interesting consequences for our planet. We live on a planet with negative entropy. So thanks again for watching.